Okay, so we're going to do a review of constant velocity and constant acceleration, and we're going to look at the coordination between the representations so that you're prepared to do homework quickly and to be ready for the quiz on Friday. So with constant velocity, remember we have a set of rules that we were able to establish, and the way we talked about those rules was in order to help us, if we were given any representation, we were able to coordinate correctly the other representations. And those are the position versus time graph, velocity versus time graph, the reference frame, and motion map. And we also want to be able to connect these to some kind of physical situation because we may be given something like I walk at a constant velocity in a certain direction for a certain amount of time. So we want to be able to talk about the magnitude of the speed and the direction. And what we saw was that when velocity is constant, we know we're going to have a horizontal line on our velocity time graph. And the way we read our velocity time graph is if I'm above the zero on the velocity time graph, I have a positive velocity. If I'm below the zero on the velocity time graph, I have a negative velocity. Because my velocity time graph cannot tell me anything about the position. This zero is relative to my speed, or the magnitude of the velocity. And the direction comes from which side of that I'm on. So in the case of a positive velocity, on my position time graph, whenever velocity is constant, I know the position time graph must have a constant slope. And the slope of the position versus time graph is the magnitude of the velocity based on its steepness, and the sign of the velocity based on whether or not it's a negative slope or a positive slope. So if I drew a steeper line that is still positive slope on the position time graph, I just have a more positive velocity. If I draw a line that was less steep, I have a lower velocity. But again, still positive because it's in a positive direction. So let's draw our motion maps for these now. According to my position time graph, I've started my position at 0. I'm moving in a positive direction with the green here, and I have a large constant velocity. Notice on the motion map I've identified the position relative to the reference frame by using a dot, and the length of the arrow is the magnitude, and the direction of the arrow is given by the head. So since all these point in the direction of the positive, I know I'm moving in a positive direction. Then corresponding, since the purple steepness is less, the velocity is less, it's still constant, but now the magnitude of my arrows decreases relative to the green, but stays constant among themselves. And then finally, the blue would be the shortest. Of the three, showing that the magnitude was less. But in each of these cases, if they travel the same amount of total distance, I need to show that on my motion map by having them end at the same position. And remember, your dot is showing your position, not the end of the arrow or vector. So let's look at an example in the negative. But before we do that, actually, there's something else I can do. Remember that since your velocity time graph does not tell you where your position is, if you start with just the velocity time graph, you get to make a lot of choices about your position, and they just need to remain consistent. So an example is this green line. I could have started here on the position time graph, and if I drew the same steepness, it would also be correct. The change I would need to make then is for the motion map for this one. I would start on the negative side, and I'm making this star just to mark which line I'm talking about here. On the negative side, I would actually start, but my motion map would essentially look the same. I'm just starting on the negative side of 0. And so again, consistency is what's important. Now if I want to look at going in a negative direction, all of the same rules apply. The slope of the position time graph is the velocity. And I know that the sign of the velocity determinant is determined by which side I'm on. And the sign of the velocity is the direction you're moving. And all that needs to stay consistent with the motion map. So now let's have a constant negative velocity. In that case, I would need a constant negative slope. If I wanted to a faster negative velocity, I would need a steeper negative slope. But I'm going to intentionally start it somewhere, I'm going to start it from 0 and go down so that we can look at how the motion map would look different. And then finally, the fastest would have an even steeper slope. Let's do this one up here. So if I want to go now to my reference frame, I want to coordinate all these. So notice what I'm doing. The steeper the slope, the greater the magnitude. But all the slopes have a negative sign, and that's why they're on the negative side of the velocity time graph. Now I need to correspond that with my reference frame when I do my motion map. So let's start with the purple. This purple starts on the positive side. And it also ends at 0, according to my position time graph. Now let's do the next fastest, the green. The green starts at 0. It has a greater velocity, so greater magnitude, and it goes into the negative side. And then finally, the largest starts on the positive side and crosses the 0 into the negative side. Greater magnitude, greater length in vector, but since they're constant, all the vectors are the same length, and I'm keeping my reference frame